because we think most people actually watch it recorded. And Friday at 5 on the west coast of the US seemed like a lot of people probably wouldn't be watching it live. So we started it early. So let's see, we got some great questions again, and let me just jump right into them. I want to share the screen. Do this.
Oh, just the one above the green.
I do this. I think we'll share the entire screen for a second. So here we go. Let's look at the questions we've got. Whoops, let's do that. Let's do that. So this is in the HTC1 course. It's a question from CTVV 3010. Is happy to be learning about recursion and is asking about whether we're learning functional programming. And the answer is yes, the BSL and ISL languages are both functional languages. The Racket language that they're both embedded in is sort of a mostly functional language. And so without kind of making a big deal out of it, we have been learning a functional programming style. Functional programming is becoming more and more important because of parallel computing. Functional programs are easier to parallelize and easier to think about when you're running using parallel computation. So functional programming languages are becoming more important. Scala is one of the big ones that's important now. So this will give you a little bit of a foundation in that, but really most of what we're learning in this course is not particular to functional programming. The exact way our code looks is functional, but the basic ideas of working systematically, of identifying information, of representing it as data, of proceeding methodically through a signature and a purpose and examples, and then the basic structure of a function in templates, and filling all that in. All of that stuff applies in any language you use and any programming paradigm you use. It's just all the details tend to look a little different. CTVV 3010's second question is, I still feel vague about the purpose of templates in designing data. So what templates really are in some senses, they're the bridge between designing data and designing a function. When we design data, we represent information as data, and we figure out what form of data definition, what form of data we're going to use to represent that information. You know, be it atomic or compound or arbitrary sized. That's designing data. Then we have an idea of a template, and it's really important to understand that all functions have a template, and all functions in any language have a template, whether you make that explicit or not. Because all functions, when you look at them, you can kind of look at it and say, well, what's the basic structure of this thing? What does it have in common with many, many other functions? And kind of separate that out from the details of this particular function. Now, what's true is that for simple functions, oftentimes what the template is it's just the unpacking of the data. And so the data-driven template rules, that's really what they're about. They're about saying, look, let's make a template that unpacks the data. So the template for operating on a compound is just ... and all the selectors. It's unpacking the data. The template for operating on a one-of is a cond that first tells which case it is and then does what's appropriate for that case. So the template for operating on a list is a cond with two cases. First, there's the empty case. And then in the conds case, I unpack the conds with first and rest. Okay? So data-driven templates are really about unpacking the data so that when you fill in the dots, you basically have the unpacked data to work with. That's data-driven templates. When we get into part 2 of the course, we're going to see other kinds of ways of coming up with templates. And we're going to see a really important idea, which is that you oftentimes, as functions get more complicated, need to take two templates to blend them together to get the backbone of the function before you fill in the details. Question 3 is, will this course have a good knowledge of data structures and algorithms if you go through the software development micromasters? So this is an interesting question. We believe that this course will prepare you for your first entry-level job as a software developer. The course, the 3 courses that we have here are not, though, algorithm strong or data structure strong. A little bit of a controversial point, but it's partly because some of us believe that the most useful point in your career at which algorithms and data structures come up is the interview. And that's not entirely true. Of course, data structures and algorithms are really important in all kinds of programming. But you'd be surprised how much more important basic software development skills are than knowing a lot about data structures and algorithms. In part because you can always learn about new data structures later and learn about new algorithms later. But I do think that if you look at the material in the career development part of the MicroMasters, so those videos that we've made available to verified learners, I think you'll get some sense of what kinds of things happen in interviews. And you might want to prepare for that, in addition to the software development MicroMasters, you might want to do another MOOC or 2 on data structures and algorithms to prep for those kinds of interview questions that are often about data structures and algorithms. If you show up at work, come back and review the software development MicroMasters, because that's what you're really going to be doing. Okay, let's switch over to course 2. And guess who has questions for us this week? Quant Pirate, who unfortunately is feeling bad that they've monopolized the office hours, and I don't think you should feel that at all. I think you're contributing great questions that everybody can learn from, so keep it up. The first question is, gee, Quant Pirate's solution to the tail recursive contain function in a binary tree, not a binary search tree. It's kind of a weird problem, okay? I'll be honest with you. We set it up to make you practice to do accumulators. But Quant Pirate's solution looks a little bit different than ours. So what I'm going to try to do is get them close to next to each other. So we'll move this out of the way, and we'll move this out of the way. Maybe we'll move them farther out of the way. So there's our solution at the bottom. Let's see if I can get them to actually line up. How come I can't do that? There's our solution at the bottom. And let me really just make it so that that's all we see. This here in the middle is our solution. So the big difference between these 2 solutions is that when we introduced the to-do accumulator, we followed the operate on arbitrary size data rule and introduced a contains/list function, this function here. And this function's job, remember this function is templated on list of whatever the a list of BT. Remember the thing I just said before about the questions that VCC had. It's templated in a way that causes it to unpack the to-do accumulator. What Quant Pirate has done instead is he has one function, or she has one function. I don't know what Quant Pirate is. I'll just say they, Quant Pirate. I'll work it out. What Quant Pirate has done is that the main function contain is templated on BT. It's templated on a binary tree, just like this function is here. But then they've stuck the template for operating on a list all unpacked in here. And so these do the same thing, but I greatly prefer this one. I greatly prefer ours because it more closely follows the one task per function rule. This function is about taking a single item from the work list and doing it, a single BT from the work list and doing it. And this function is about processing the work list itself. And the real decision point was way back here when we first introduced the to-do. We added this contain/list function for processing the to-do list, in part because of the operating on arbitrary size data rule, and in part because of the one task per function rule. Quant Pirate's next question is about a great problem called the max entries problem. So this is a graph problem, and in a directed graph, it's easy to know for a given room where you can go to from that room. But when the arrows on the graph just have arrowheads at one end, it's hard to know where you'd be sitting in a room and you can't quite see all the doors coming into it. The graph doesn't naturally give you that. So you have to work to produce that information. And this is one example of how you might do that. This function basically is about, in a graph like that, find the room that has the most arrows coming into it. In our solution, what we do is that we walk through the graph in the normal way that you have to do for a graph. So we've got a visited accumulator and a to-do accumulator to make sure that we're doing a tail recursive traversal and that we don't go around in circles. And we don't visit rooms twice. And our result so far is the number of exits leading to each room so far. So room and exits is a room and the number of exits to it. So when we get to the very end, we have a list of room and exit compounds that tell us for each room how many other rooms lead to it. And then when we get done, we just, where's the call to pick max? We just call pick max to pick one of those that has the biggest exits. Quant Pirate has a similar design. It's just a little bit different. In Quant Pirate's version of it, what is accumulated is a list of the rooms that were exited to. And this list is allowed to have duplicates in it. Okay, it's every time you found an exit, you put the room that exit was to on this list. So it's slightly different than the rooms you went to, because the way that the graph traversal code works is you'll never actually go to a room more than once. This is a list of the rooms that you found an exit to. So this will have duplicates in it. And then what Quant Pirate's solution does at the very end is it just goes through that list and counts up for each room in it how many times it appears. And as it goes through, it's picking out the one that has the largest number of exits to it. So these are really very, very simple. This is going to end up with a list where rooms appear multiple times, and that's how you know how many exits there are to them. Our solution is going to end up with a list in which rooms only appear once, but there's a natural number associated with them, counting how many exits there are to them. So in some sense, our version has done a little bit more work up front than Quant Pirate's version has done, but they're essentially the same solution. Both are fine. And one more question from QuantPirate. This is a very nice little question here. These are all very nice little questions, but this one's quite fun. So QuantPirate points out that when we did take, and we said, you should do take as a 2 1-of problem. And the ways in we did that, this function take takes a number and a list, and it pulls off the first n elements of the list. She might be back. Do you want to go check for that?
Okay, sure.
Sorry, coming back. So what take does is it pulls off the first n elements of the list. And so we did that as a 2 1-of because we took ln, that's a 1-of, and we took the self-referential data definition for natural numbers, so that's a 1-of. And we ended up with this function that basically counts the number down to 0 and takes rests of the list. And once the number reaches 0, it stops taking things off the front of the list. QuantPirate did it an interesting different way. Which is instead of counting n down the way we did, we're counting n down. See this sub 1n? QuantPirate takes a new number, an accumulator, 1 position. He starts at 1 and counts it up. See this add 1 position? So we're counting down. QuantPirate's counting up. And because we're being very careful about using the self-referential data definition for natural, we do it as a 2 1-of. Because QuantPirate is counting up, that's not the sort of natural recursive version of counting down a natural number. So QuantPirate chose not to do the 2 1-of. These two solutions are otherwise quite similar. Although note that we've got all the data-driven template-based code in the questions of a cond. And here there's some of it in the cond and some of it in the if. But these solutions are both fine. You know, a practicing programmer, okay, when you have a 2 1-of that has this structure where so few things can happen, basically in the whole 2 1-of, only 2 of the cases can happen, a practicing programmer wouldn't build out this whole table for this because this simplification is relatively straightforward. I would still prefer to, I think, see this simpler code rather than introduce the separate number that counts up, but either are fine. And I think that's the last of our questions for this week. Do we have any more?
Do you want to just refresh?
Oh, let me just refresh in case someone has come online.
Just do that.
And it is none in this course, so let me go to the other course. No. So I think we'll end there. And listen, if it turns out that there was a bunch of people who were waiting till 5 o'clock on Friday on the west coast of North America, because they really wanted to have their first hour of the weekend being office hours, and now they're going to be disappointed because we're not there with them, then we'll apologize to those people. But I think when we scheduled, Sazi and I had this fantastic idea that we were going to provide some more variety in the office hours so that it didn't always favor the North American people. And I think it was a brilliant idea, but I think somehow we didn't understand that one of the times we picked was Friday at 5. So we will continue to vary the office hours, but maybe we will sort of some kind of filter function on the list of office hours that we come up with to throw out the ones that maybe kind of aren't going to be most attractive. At any rate, we'll see you again in a couple weeks. And thanks for all your hard work and your great questions. And in the meantime, we'll see you on the discussion forums. Bye-bye.